Hello everyone. Hello everyone. So welcome to today's session, that is session number 11. So in this session we will be solving the doubts related to the week of the related to the content of the week number 11. That was mainly related to the view factor in this radiation topic. So in this week, the course content had discussed about this view factor, then diffuse gray surfaces in an enclosed cell method, and then there were these three chapters that basically discussed how to solve the numericals related to radiation by using the concept of this resistance. So today we will be solving numericals related to it. But if you have any doubts related to the previous weeks or the current week, you can ask me, or else we can start with solving the numericals. So yes, in the last class, in the earlier classes, we had defined this view factor, that is Fij. That is nothing but basically it is a geometric parameter or geometric factor, you can say, and it is defined by this integral. So this quantifies that the fraction of energy that leaves surface I and reaches surface J. That is how we interpret this Fij term. Then we have these important relations. So the first one is known as reciprocity theorem, that says that, let's say if we are having two surfaces, 1 and 2, and then for this surface, if the view factor for the radiation that leaves 1 and reaches 2 is F12, similarly vice versa it is F21, and if the area of 1 is A1, area of 2 is A2, then for this system we can write the reciprocity theorem as F12 A2 is equal to, you can write this as A1 F12 is equal to A2 F21. So using this, we can find the values of this view factor F12 or F22 along with using the summation rule. So the summation rule states that the summation of Fij equal to 1, that implies F11 plus F12 is equal to 1 for this system. Similarly, if we have more than two surfaces, then we can write F11 plus F12 plus dot dot F1 and surfaces is equal to 1. So these two rules will be useful in order to find the view factor for different kind of geometries. So yes, for example, in this system whereby we are having two cylinders. So for cylinder 1, the inner surface, the outer surface is the reflective one, and for cylinder 2, the inner surface is the reflective one. So if I have to write F12, that is the fraction of radiation that leaves surface 1 and reaches surface 2, so I can write that the entire radiations will eventually reach this surface 2, that is why surface 1, that's why you can write F12. Similarly, if this is my surface 1, so none of the radiation that leaves this surface surface 1, will reach this again, will leave the same surface. That is, no radiation will be in this manner. That is why you can say that F11 is 0. But ultimately, this will get reflected. After reflection, it can reach, but that we can't term it as F11. It will come into this F1, F12 or F21, whatever we define. And then for arbitrary geometries, for example, if we are having a plate of width Wi and width Wj, then we can define this Fij by using this formula. So these formulas usually come from this equation. So you can use this equation in order to find the view factor for any given geometry. In the reference book, we have the table available for various kind of sample geometry. So we will be straight away using that table if we encounter any different geometries. Then this we also saw that the radiative resistance, basically if you have tried the heat exchange due to this radiation, then we can write using these equations. So over here the equation is written in terms of this rate, the driving force upon resistance. So this denominator we call it as radiative resistance, and the numerator we call it as the driving potential for radiation. So similarly, if we have multiple resistances in series or parallel, then we can just use the concept of resistance over here also, where the radiative resistance will be given by this term. Then this radiosity formula was already discussed in the previous class. So similarly, if we have multiple sources of this multiple geometrical resistance, that is, we are having different kind of surfaces, then the overall resistance, then the overall heat transfer rate, we can just write it using this summation, that is J1 minus J2 upon this kind of summation. This we will see once we solve the numericals. Then again, we can use the concept of this radiation in order to solve the questions related to the radiation. Similar to this one. So over here, you can see that if we are having two surfaces, 1 and 2, so due to this there are different geometries, or due to this view factor, we will be having one radiation, and due to the inherent the radiation resistance across both of these individual surfaces, we will be having this resistance. So ultimately, we just take the summation of all this resistance and put it in denominator, and the driving force of the radiation will be given by this law. So this is how we use it. Then there was this concept of radiation shield, whereby we are having two surfaces which radiate energy, and then we keep a radiation shield, or basically you can say any plate or any object of some certain thickness between them in order to alter the radiation. So such kind of shields are known as radiation shield. So schematic of this is also shown over here. So we will again see one numerical related to the radiation shield. This we already saw. So yes, we can try solving the questions for today's class. If you have any doubt, you can just unmute yourself and ask, or just write it in chat box. So this is question number 1. So whereby we have been given a geometry of certain shape, and we have been asked what are the values of F12 and F21 for the following configurations for a long open channel using the reciprocity theorem and other basic shape factor relations. So over here, we have been given a long open channel whose cross section is shown in the figure. So basically, ultimately, this will be a very long channel. And for this, we have been given different surface. So the base surface is A1. Base surface is 1 with area A1. The curved one half of the curved surface is A2. The other half of the curved surface has area A3. And for that, we have to find the view factors F12 and F21 for this given geometry. So let's try solving this question. So this is question number 1. So we studied 2 rules. So the first one was summation rule. So for this system whereby we are having two surfaces, 1, 2, and 3, we can write the summation rule as F11 plus F12 plus 1, 3 is equal to 1. Now over here you can see that this is a flat surface, that is F, the surface 1 is flat surface. So for that surface we can see that this any radiation leaving this surface will not eventually bounce back to this to this will again not reach this surface. So that is basically, we can also see that this surface can't see itself, whereas the other two surfaces A2 and A3, they can see itself, so they will be having some values of F21 or F23, whereas they will be having some value of F22 and F33, whereas for the surface 1 with an area A1, the value of F11 will be equal to 0. So we can ultimately write this F12 plus F13 is equal to 1. Now again, we can, from the diagram, we can see that both of these surfaces 3 and 2 are symmetrical. So basically they are just a part of this, they are just a half part of this, half of the cylinder. So we can say that the geometry of both of these objects is similar. That is, we can also write that since the geometry is similar, the view factor will be similar. That is, F12 will be equal to F13. So from this equation, we can write F12 is equal to F. So both will be equal to 0.5. That is what we can write. Now, in the given question, we have been asked to find F12 and F21. So F12 we already found over here is 0.5. Since we have to find F21, we can use the reciprocity theorem that states F1 F12 is equal to A2 F21. From here, F21 will be A1 upon A2 into F12. Now, this area is, the area A1 is 2 meter into, if it has some fixed length of L, so the area of base will be 2 times length L. Similarly, the area of A2, that is this segment. So the circumference of this circle is 2 pi r, and for this time the half of it will become pi r, and again this part will have the circumference of pi r by 2. So that is, we can write this as pi, the radius is 1 by 2 into length L. So we can cancel this out, and this will become, okay, F12 is 0.5. So this will become 4 by pi into 0.5. So this you can calculate 4 into 0.5 divided by 3.4. So this will be 0.636. So F12, the value of F12 was 0.5, and the value of F21, we calculated it as 0.636. So for this simple geometry, we can just use both of this formula of reciprocity theorem as well as the summation rule in order to find the view factor. So this is the sample solution. So now for other different kind of geometries, we have this table number 13 in the book that you can use. So this formula I had already kept in the slide. Similarly, for other kind of geometry whereby we are having parallel plates of equal width and common edge, we can write this view factor F ij is equal to 1 minus of sine alpha by 2. For this, we can write, so this, the formula for this can be derived using the earlier equation. Basically, this equation you can use in order to find the view factor of any geometry. So the more derivation you can find it in the book. But right now we'll be using just this formula to solve the next question. So this is again the similar question whereby we have to use the given formula in order to find the view factor. So we have been asked to evaluate the view factor F12 for the sketch given below. So if you see over here, we are having a surface 1 with an area of A1 and let's say length of 4 meters. Then we have the surface 2 so this is our surface 2 and the area for this is A2 and this again diameter is 4 meter. Now we can see that whatever radiation will leave this curved surface, it will always pass through this area of this diameter, you can say 4 meter. So basically this radiation will be restricted by this area of this diameter of 4 meter, diameter whatever you can say, length of 4 meter. So for that, the effective area through which radiation will occur will be due to this 4 meter. So this case is will become similar to the case whereby we are having two plates that are kept at an inclined angle. So this is again similar to this question whereby we are having an alpha. So both of this diagram are geometrically equivalent if we consider the radiation. So for this system, in the earlier slide, we saw that the view factor F12 will become 1 minus sine of alpha by 2. Now in this case, the angle between both of this is 30 degree. So we can just write it as 1 minus sine of 15 degree in order to find the view factor. This will be 1 minus sine 15 is around 0.74. So the view factor for such a curved surface and then horizontal plate will be 0.741. So if you have any doubt, you can just write it in chat box or unmute yourself and ask. Then this is the model solution. Now let's move on to the third question. So in the third question, we have been given that a drying oven consists of a long semicircular duct of diameter 1 meter. Materials to be dried cover the base of the oven while the wall is maintained at 1200 Kelvin. What is the drying rate per unit length of the oven if a water coated layer of material is maintained at 325 Kelvin during the drying process? Black body behavior may be assumed for water surface and the oven wall. And then we have been given HFG is equal to 2.378 into 10 raised to 6 joule per kg. So in this question, we have been given a drying oven. So this is basically a drying oven, and over the base we are having the material that is to be dried, and for that we have been asked to find the drying rate per unit length of oven. That is basically we have to find the mass flow rate, or basically the amount of water evaporated per unit length of this oven. That is what we have been asked to find. So let's try solving this question. So over here, we are having two surfaces. So the first one is this curved surface, that is 1. The second surface is the bottom surface, 2. So there will be radiation exchange between both of this surface, so that we can write it as Q12, and due to this radiation, water will get evaporated from this base. So that net heat exchange due to evaporation, we can write it as m dot into HFG. So this is the m dot that we are supposed to find. But for that, first we need to find the overall radiation heat exchange between these two surfaces. So over here, we have been given that we have to consider both of these surfaces as black body. So for black body, we can straight away write for Q12 as area times mu factor F12 Stefan Boltzmann constant upon T1 raised to 4 minus T2 raised to 4. This is what we can write. Now we don't have the value of this mu factor F12. So first we need to find the value of this mu factor F12, and then we can later on calculate it. So we know that we can write F12, A1 F12 is equal to A2 F21. Now again, this surface 2 is a flat surface, and as seen in the previous two questions, we can write that F22 will be equal to 0. So basically, ultimately, we can write that F12, F21 plus F22 will be equal to 1. So from this, we can write F21 will be equal to 1. So if you put it over here, we can get F12 is equal to A2 upon A1 into 1. Now the area of base will be diameter times, if the length is L, so the area of base 2 will be A2 is equal to diameter into L. Similarly, the area of this curved surface will become 2 pi r pi, basically that will become pi d upon 2 into L. With this, we can cancel this out. So this 2 upon pi will give us the mu factor, that is F12 will be 0.637. Now we can use this F12 over here in order to find this Q12, and then we can again use it over here to find the value of m dot. Let's just do that. So Q12 will become A1 is pi T2 into L. F12 we calculated it as 0.637. The value of sigma is 5.67 into 10 raised to minus 8. T1 is given as 1200 Kelvin. 1200 raised to 4 minus of T2 is given as 325 Kelvin. And this will ultimately be equal to the rate of evaporation, the heat rate due to which evaporation is occurring, that is basically m dot into HFG. Now in the question, we have to find the drying rate, that is basically m dot upon L. So we can write this as m dot by L is equal to this entire calculations upon HFG. So let's just calculate this term first. So this entire term becomes 1.16 is 2 by and if we divide this by the value of HFG is so if you calculate this out, this will come around 0.04916. So that is the drying rate from the given oven will be around 0.0492 kg per second per unit length of the oven. So yes, this, let's again see the model solution. So this is the final solution whereby we were asked to find the drying rate. Now let's see another question related to the same U factor radiation. So in this question, we have been given consider coaxial parallel black discs separated a distance of 0.2 meter. The lower disc of diameter 0.4 meter is maintained at 500 Kelvin and the surroundings are at 300 Kelvin. What temperature will the upper disc diameter 0.2 meter achieve if the electrical power of 17.5 watt is supplied to the heater on the back side of the disc if the discs have two black surfaces? So over here we have been given two surfaces, 1 and 2, and in this surface 1 we are providing an electrical power of 17.5 watt, and we have been asked to find the temperature that this upper disc will achieve as a result of the heat exchange due to radiation that we have been asked to find. And for the given system, we have been given the view factor between F12 as this formula. That is F12 is equal to 1 by 2 into S minus of square root of S square minus 4 into R2 minus R1 whole square, whereby S is defined by this formula and R is the ratio of the radius of the object upon the length between both of these two surfaces. So using this formula, you can first calculate the value of the required view factor. So once you have this required view factors, then you can straight away use the energy balance in order to find the desired temperature. So over here, due to this electrical power that is PE, we will be having the radiations that is basically F12 that is between these two surfaces. Also, we have been given this, the temperature of surrounding has also been given. So we can treat this as an object 3. So we will be also having the radiation exchange between F13. So we also need to find this F13 as well as this F12. So basically, if we write the energy balance, this will become A1 F12 sigma T1 raised to 4 minus T2 raised to 4 plus due to this surrounding, we will be having A1 F13 sigma T1 raised to 4 minus of T3 raised to 4. So this is basically surrounding. So from this, we can calculate the electrical power is given, but from this we can find the desired temperature. That is we can find the value of T1 from this entire equation. So try solving this, and I will try solving this, and I will again share the solution with you. So for such complex geometries, the formula for the view factor should be given. For simple geometries, whereby you can just calculate the areas, you can do that on your own. So try solving this question. I will again share the solution in, let's say, 3 minutes. So let's try to solve this question if you're not able to solve it. So as I mentioned, you need to find the required view factor. So that the view factor that you required, you can get, you can first write the energy balance, and then you will get an idea of what all view factors that you required. So the energy balance will be equal to, so basically you can write this 17.5 watt, 17.5 basically will be equal to the radiation to the surrounding plus the radiation to this surface. Over here, we have been given that the disks are the black surfaces, so we are treating them as black body. A1 F1 to sigma T1 raised to 4 minus of T2 raised to 4, and for surrounding it will become A1 F13 sigma T1 raised to 4 minus of T surrounding raised to 4. We don't have the value of T1, but we can again rearrange this equation in order to find T1. So this will become A1 F1 to sigma T1 raised to 4 plus A1 F1 to sigma T1 raised to 4 minus of, you can write this as A1 F1 to sigma T2 raised to 4 plus f1 plus f1 plus 4. So from this is 17.41. You can write p1 plus 4 is equal to 17.51 plus a1 plus 4 plus a1 plus 4 on a1 plus a1 plus a1 plus 4. So ultimately you can use this equation in order to find T1, but before that we need to find these view factors F13 and F12. So for this surface, that surface 1, we can write F11 plus F12 plus F13 is equal to 1. That is, we can write, again we know that F11 will be equal to 0. So this will give us F12 plus F13 is equal to 1. Now F12 we can calculate by using this formula, and then that we can put over here in order to find the value of F13. So let's just first calculate the value of F12. So over here, surface 1 is the smaller one with diameter of 0.2 meter. That is R1 will be 0.1 meter. R2 is 0.2 meter. So basically from here we can write R1 is equal to R1 upon L, R2 is equal to R2 upon L. The distance between both of that is 0.2 meter, whereby L is equal to 0.2 meter. So R1 will become 0.1 upon 0.2 will be equal to half, that is 0.5. R2 will become 0.2 upon 0.2, that is equal to 1. So you can calculate this value of S. So S will become 1 plus Rj, that's basically R2, 1. Ri square is 0.5 whole square will become 0.25. So this will become 1 plus 8. This will be equal to 9. So the value of S is 9. Now we need to put it over here. F12 will be equal to 1 upon 2. The value of S is 9 minus 81 minus 4 into R2 upon R1. It's 2. 2 whole square will be 4. So this you can write it as 9 minus 9 minus of 16. So the value of the view factor F12 comes around 0.4689. Now in order to find the value of view factor F13, we can just subtract it from 1. That is, we had seen F12 plus F13 was equal to 1. That implies F13 will be equal to 0.531. Now we can put these values in this equation. So now we just need to replace the values over here. So T1 raised to 4 will be equal to 17.5 plus the value of A1 we need to calculate. So the value of A1 will be equal to so these are d, so we can just write it as pi d square by 4 pi r square is so this will be the value of area A1. So you can just write this as 0.0314 into F12 was 0.468. Let's just call it as 0.47. Sigma is 5.67 10 raised to minus of 8. T2 raised to 4. T2 we have been given as 500 Kelvin and T3 is 300 Kelvin. 500 Kelvin raised to 4 plus A1 is again 0.03141 into F1 3.5311. Sigma is 5.67 minus 8. TS is 300 raised to 4. 1 minus 8. So now you can try solving this, and if you solve this, the value of T1, if you simplify this, the value of T1 should come around 456 Kelvin. That is the temperature of the upper disk will be around 456 Kelvin. So you can just simplify this and this should be the final answer. So if you take a look on the model solution, so yes, the final answer should come around 456 Kelvin. So if you have any doubt in this question, you can ask me, or else let's try solving this question number 5. So again, read this question number 5. This is again similar to the previous questions, whereby we had used this energy balance in order to find the, we have used this energy balance in order to find the temperature. So over here, we are having convection mode of heat transfer also, and then we have been asked to find whatever questions that has been asked. So try to read this question. I will solve this in a couple of minutes. So let's try to solve this question. The question states that a diffuse gray radiation shield, a diffuse gray radiation shield of 60 diameter and emissivities epsilon 2 I is equal to 0.01 and epsilon 2 O is equal to 0.1 on the inner and outer surfaces respectively is concentric with a long tube transporting a hot process fluid. The tube surface is black with a diameter of 20 mm. The region interior to the shield is evacuated. So basically over here we are having vacuum. The exterior surface of the shield is exposed to a large room whose walls are at 17 degrees Celsius and experiences convection with air at 27 degrees Celsius and the convection heat transfer coefficient of 10 watt per meter square Kelvin. Determine the operating temperature for the inner tube if the shield temperature is maintained at 42 degrees Celsius. So we have been given the system of concentric cylinders, and for that we have been asked to find the temperature of this inner tube. This temperature we have been asked to find if this temperature is maintained at 42 degrees Celsius, and then we have been told that this surface, both of the inner as well as outer surfaces of this outer cylinder, uh, outer cylinder will emit radiations. That is we have been given, and again we have been given this that the object is a diffuse gray radiation shield. So in the previous questions, the surfaces that we were considering were black body, whereas in this case we have been given this gray body. So for that the net heat exchange to radiation will be given by these equations. That is basically Q12 will be equal to A1 sigma 1 upon T1 raised to 4 upon T2 raised to 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 I upon epsilon 2 I upon D1 2 D1 upon D2. So this will be the net heat exchange due to radiation. But again, we have been given that the outer surface will also emit radiation, and for the outer surface, we have also been given the convective heat transfer coefficient. So if we are considering this as surface 1, this is surface 2. So from surface 2, we will be having this apart from this radiation that is generated, we will be also having this convection. So the Q convection will become H times, if the area is A2, then T2 minus of ambient air, that is T infinity. And again, radiation will be emitted from this. So Q radiation will become simply epsilon 2 A2 sigma T2 raised to 4 minus the surrounding temperature is T surrounding raised to 4. So over here, if we consider this radiation, then the radiation will be due to this wall that is present over here. So T surrounding, that is T surrounding, no, not T surrounding, T surface here created at 17 degrees Celsius, whereas the ambient air temperature under which the convection will take place is around 27 degrees Celsius. So ultimately, this net heat exchange will be equal to Q convection plus Q radiation. So you can use this in order to find the overall heat exchange, that is basically Q12, that is what you can find. So let's see the solution for this. So we saw that the overall heat exchange Q12 will be equal to Q convection plus Q radiation. That is, you can write this Q12 as, so Q12 is given by this equation, whereas Q convection we saw it HA2 T2 minus T infinity plus Q radiation is given as epsilon 2. Since radiation is occurring from this outer surface, we will take the emissivity of outer surface as well as the area of the outer surface. That will remain same, A2 upon T2 minus of Ts whole raised to 4. Now we have been asked to find the value of T2 over here. No, what have been, we have been asked to find the value of the inner tube. That is, we have been asked to find the value of this T1. So we can just equate this equation in order to find T1, that is equal to A1 sigma T1 raised to 4 minus T2 raised to 4 1 plus epsilon 1 minus So from this equation, you need to put all the relevant values and then find the value of T1. So let's just first calculate this term. So the value of epsilon 1 is given as 1 and epsilon 2. Basically, this is epsilon 2i. So epsilon 1 is this 1 and epsilon 2i is 0.01. So this will become 1 plus 1 0 1 1 2 is 2. So this denominator should come. So this comes around 67. So let's just find the other parameters. Let's just calculate this term. So the value of H is 10. Then the outer area is within this. So what you can do is just take this area common and h will be 2 tan into T2 minus of T infinity. T2 I think we have been given as T2 sequence, which is minus 15 plus epsilon 2 is 0.21 into plus 73 raised to 2 minus of the surrounding is 17 plus 3 raised to 4. This will come around so this was 42 minus 27, that was 15. 150 plus this will come around 15.72. This will
నువ్వు కూడా
165.73. So this will give you 11.82 even just minus of this is this on So if you solve this, eventually the value of T1 should be equal to, I have written answer is 744 Kelvin. I might have made some calculation mistake over here, but if you just use this formula, the final answer should come around 744 Kelvin. So again, as in the previous question and in this question, we used basically the energy balance along with this radiation heat exchange in order to find the temperature of whatever systems we were given. So over here I had made a mistake. It should be 1/3. This, so yes, you can try solving this, and ultimately this will become 34. So if you solve this, as mentioned in the steps, the value of temperature will be equal to 744 Kelvin. So the temperature that was asked is equal to 744 Kelvin. Now we can take a look on the next question. So in this question, we have been given a circular ice rink 25 meter in diameter is enclosed by a hemispherical dome 35 meter in diameter. If the ice and dome surfaces may be approximated as black bodies at 0 degrees Celsius and 15 degrees Celsius, what is the net rate of radiative transfer from dome to the ring? And then we have been asked to consider them as the black bodies. So for this system, we have been asked to find the net rate of radiative heat transfer. So if we take a look on the diagram, it should become, we have been given a circular ice rink. So basically this is our ice and it is enclosed by an hemispherical dome. So for this, the diameter is 25 meter, and for the dome, the diameter is 35 meter. Then the ice and the dome surface are approximated as black body. So the temperature of ice is 0 degrees Celsius and the temperature of the dome is 15 degrees Celsius. And then we have been asked to find the net rate of heat exchange from dome to ring, which will be considered as 2 and as 1. So we have been asked to find Q21. So since these are black body, we can write this as A2 F21 sigma T2 raised to 4 minus T1 raised to 4. Now we need to find this value of F21 and F21. So for this system, we can again write this as F12 plus F11 is equal to 1. Since this is surface 1, can't see itself, so F11 will be equal to 0. So we can write this F21 will be equal to 1, F12 equal to 1. So now in order to find F21, we can write the reciprocity theorem, that is A2 F21 is equal to A1 F12. F12 is equal to 1. So that is, we can write this is equal to A1. So we can just replace the value of A2 F21, that is basically this, by the value of A1. So this will be equal to A1 sigma T2 raised to 4 minus of T1 raised to 4. For this, the area will be pi by 4 d square. Sigma is 5.67 n raised to minus 8. The temperature RT2 is 15, that is 288 raised to 4 minus of 273 raised to 4. So you can calculate this. This is 12. So this will come around 491 into this is equal to 3.6 goes to 4. So the net heat exchange between both of these black bodies will be equal to 3.6981 into 10 raised to 4 watt. So again, this was a straightforward question since we were given that both the objects were black body. So this is the model solution that you can see. So now let's move on to the question number 7. So in this question, we have been given consider two large diffuse gray parallel surfaces separated by a small distance. If the surface emissivities are 0.8, what emissivity should a thin radiation shield have to reduce the radiation heat transfer between the two surfaces by a factor of 10? And then we have been given certain assumptions. So basically in this question, we have been given two parallel surfaces. So this is surface 1, this is surface 2. And then we have been told that we are inserting a radiation shield of certain emissivity, due to which the net heat transfer rate decreases by a factor of 10. So basically, Q without shield upon Q with shield will be equal to, so without shield, the radiation will be equal to, will be higher. So this will be basically equal to 10 upon 1. So this is without shield and with shield. So the net rate, the heat exchange, if we increase the, if we introduce the shield, it will basically becomes 1/10th time of that. So let's see how do we solve these questions whereby we have this radiation shield. So let's consider the situation whereby we don't have any shield. So in that case, we will be having two surfaces, 1 and 2. For surface 1, the emissivity is 0.8. For surface 2, if the emissivity is emissivity for this case is also 0.8. Then for this surface, we can write the overall heat exchange as Q12, let's just call it as without shield, WO, will be equal to A1 sigma T1 raised to 4, T2 raised to 4 upon, there will be this resistance 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Now, if we introduce a shield in this, so if we take a look on the resistance diagram, so see, so the additional resistance will be introduced as shown in this equation. So basically, the overall resistance will be equal to Q12 is equal to A1 sigma T1 raised to 4 minus T2 raised to 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 plus 1 minus we are having epsilon 321 1 epsilon 31 plus 1 minus epsilon 32 epsilon 32. So this is with shield and this is without shield. Since we are given that both the surfaces are similar, so that is epsilon 1, epsilon 2, both the surfaces are similar, so we can treat that epsilon 31 will be equal to epsilon 32 for this case. So this will be equal to A1 sigma A1 raised to 4 raised to 4 1 plus epsilon 1 plus epsilon 2 plus 1 upon epsilon 3. So we are treating this as epsilon 31 is equal to epsilon 32 minus of epsilon 31 minus of epsilon 31 upon epsilon 31. So this will come around A1 sigma A1 raised to 4 upon A2 raised to 4 1 epsilon 1 plus 0 epsilon 3 this. So we have the formula for the heat exchange without shield and with shield, and then we have been given that their ratio is equal to 10. That is, if we take the ratio of both of this term, the numerator will get cancelled out and we'll be left with the fraction that is 1 upon epsilon 1, 1 upon epsilon 2 plus 2 upon epsilon 31 minus of 2 upon this term 1 upon epsilon 1, 1 epsilon 2 minus of 1 is equal to 10. Now the value of epsilon 1 and epsilon 2 we have been given, and then we have been asked to find the value of epsilon. We have been asked to find the emissivity, that's epsilon 3. So epsilon and epsilon 2 both are equal to 0.8 plus 2 upon epsilon minus of 2 upon 1 upon 0.8 will be equal to 1.25. 1.25 will be equal to 2.5 minus of 1. So this is equal to 1.5. Is equal to 10. So this will be equal to so if we solve this, the value of epsilon 3 will come around 0.1379. That is, the emissivity of the shield will be equal to 0.13, will be equivalent to 0.138. So So this is the model solution. You can take a quick look on it, and then we can move on to the last question for the day. So now let's move on to the last question. So this is question number 8, and we have been given the end of a cylindrical liquid cryogenic propellant tank in free space is to be protected from external solar radiation by placing a thin metallic shield in front of tank. Assume the view factor FTS between the tank and the shield is unity. All surfaces are diffuse and gray, and surroundings are at 0 Kelvin. Considering the additional assumption that the resistance of the shield for conduction is negligible, answer the following. What is the temperature of the shield Ts, and what is the heat flux to the end of the tank? So in this question, we have been given this cylindrical propellant tank, and then we are having this solar radiation coming from the far away. So in order to prevent the cryogenic tank from this solar radiation, we are putting a shield over here. And then given the following values, we have been asked to find the temperature of this shield Ts and the heat flux to the end of the tank. This is the heat flux over here. So in order to solve this, you can write the energy balance and try solving this. So if you consider that, let's consider that this is my tank and this is my surface of the shield, that is shield, tank, and then we have been given that we will be having the solar radiation over here. So the amount of solar radiation absorbed by this surface, so in this we have been given a diffuse gray surface, so this will be equal to, if the absorptivity is alpha, then this will be equal to alpha times of Gs. The temperature of this due to that will become Ts, and ultimately due to this radiation there will be an overall heat exchange between this, so between tank and shield, so that is we can write it as QST. So again, due to the temperature, due to the any temperature, this Ts, it will again have this radiation, Q radiation. So basically the overall heat exchange QST, you can write that as QST will be equal to, the net heat exchange will be equal to Q radiation. No, basically it will be equal to this alpha times GS minus of Q radiation, alpha S GS minus Q radiation for this will be equal to epsilon 1 sigma Ts raised to 4, and QST, that is the heat exchange between both of the surface. We can write that as sigma Ts. So we have just cancelled the area since the area for the system will remain same. Temperature of the shield Ts raised to 4 minus temperature of the tank Tt raised to 4 upon the resistance will be 1 upon epsilon 1 plus 1 upon epsilon 2 minus of 1. And then in this question, we have been asked to find this value of Ts. So have we been given the value of emissivities? So in the figure, we have been given that the emissivity of the tank is 0.1 and the emissivity of shield is 0.05. Now, since this is a diffuse gray object, we can say for this gray object, we can say that the absorptivity will be equal to the emissivity, that is basically this alpha S will be nothing but it will be epsilon 1, that is equal to 0.5. So now we can just replace these values as epsilon 1. So we have to find this value of Ts raised to 4. So we can just write this as epsilon 1 Gs is equal to sigma Ts raised to 4 1 plus epsilon plus epsilon minus f1 epsilon 7 raised to 4. So if we simplify this in order to write the equation in terms of Ts, this will be equal to epsilon 1 Gs plus sigma T1 goes to 4 upon epsilon 2 minus of 1 upon sigma common over 1 minus of 1 is epsilon 1 is equal to plus raised to 4. So now you just need to put the values over here and then you can calculate the value of Ts. So epsilon 1 and for tank, that is epsilon, for shield, that is epsilon 1, we have been given it as 0.05. So let's just this denominator will be equal to 1 upon 1 plus 0.01 plus 1 plus 0.5. So this value you can put over here. So the value of GS we have been given as 1250. That is 1250 into sorry, one is 0.05 plus 5.6 7 1 10. So over here, the first surface is our tank. So this will be 0.1. Temperature of tank is 100 Kelvin raised to 4 on 1 plus this calculated plus 1 divided by so if you simplify this, the value of TS from the answer that I'm having will come around 338 Kelvin. So, and then in the second question, you were asked to find the heat flux. So heat flux is nothing but basically this parameter, that is QST, that is heat flux, is equal to sigma Ts raised to 4 minus T tube raised to 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So this again you can calculate it as 5.67 minus 8. The temperature of this surface, this we calculated it as say 38 raised to 4 minus temperature of tube, that is cryogenic, is 100 raised to 4 upon the same term, that is 1.05 minus 1. So if you calculate this, the value of QST, so the heat exchange, the overall flux, since we're dividing this by area, the flux will become 25.3 watt per meter square. That is, the overall heat flux to the end of the tank will become 25.3 watt per meter square. So this is our final solution. You can take a quick look onto this. So yes, that was all from the previous week numericals. If you have any doubt in the previous assignments, you can just ask me, or else we can end this session. So in today's class, we discussed the questions related to view factor and the other questions whereby we had to find the radiative heat exchange between two black bodies or diffuse gray bodies. In case of diffuse gray bodies, we have this parameter of epsilon, and then we also saw these systems whereby we have these resistances. If you have any doubt, you can ask me. I will be here for more 10-12 minutes, and then we can end the session. I am here. If you have any doubt, you can just ask me. I'm just turning off my camera.